Good morning, good morning, good morning. Um, Today, what I want to look at today is something called magnetism. Now, magnetism is used in everyday life and everyday living. But one of the things we use magnetism for in electrical trade is for motors, generators, alternators, and so forth. So magnetism has quite an effective role in our everyday unexpected living. Now, it I had a thought: how is it possible that we can, if we can create magnetism to an extent, why can't we use it as a magnetic force or a field around a vehicle, for instance? But that's just my imagination running away with me today. Okay. Right. What I want to do is, again, we're going to look at magnetism, and again, remember that you're not going to see what I'm looking at, but you'll need to look at the video specifically called Magnetism 1, Session 7. Okay. And that is what I'm going to be talking about today. Okay. Let me just get organized. Okay. Now, you will always notice that no matter how you try to get organized and ready for these things, it never works the way you think it's going to work. But just bear with me. We'll be bored for uh, however long it takes. Let's have a look. Let's have a look. Hang on. Okay, I gotta check. Gotta clean you down first. Take you out. Yes, take you out. Delete you. Delete you. Okay. Sorry for me. A second. Okay, thank you. Okay. Right, let's see what if I can get into this thing now. Okay. Okay, I don't want to get you too mixed up. Okay. Now, one of the things here is the other day I did a video and only to find that the top part of the video wasn't coming into view. Okay, so bear with me. Oh, that's okay. You could be as patient as you like, but it's my video, so you can speed it up as you wish, whatever. Right. What I want to look at is magnetism, and this is we're looking at session 7. And let me just take this off for a moment. Okay. Again, here, let me go back. Looking at sitting gills. Okay. You cannot miss it. Okay. I remember the days when Sitting Gills was just an open enterprise, and it wasn't a money making business as it is now. Okay. And I recognize that certain things you now have to pay for. But remember, training and education and an apprenticeship is for life. It serves you for life. You could change, diversify, and divert to other areas of work if the environment changes. But remember that once you have been trained, that is a lifelong process. Okay? Right. Aims and objectives in this session: to understand how magnetic fields are created, to understand the direction of magnetic fields, to understand how to use magnetic fields. Okay? Okay. Right, again, just to recap, Sitting Gills, don't need to go any further on that. And we're looking at session 7, magnetism. I repeat, session 7, magnetism, okay? Aim and objectives. Again, I'm just recapping here, okay? To understand how magnetic fields are created, to understand the direction of magnetic fields, to understand how to use magnetic fields. And yes, I forgot to turn on my camera in the first session, so yes, I know. Okay, you smart Arabs. Okay. Yes, I know. I was just trying to be clever. Okay, I accept that. Now here, this is a lot of the work you've done already, which is on video. Look back at the work. Make sure you understand it before you begin to go any further. Okay. Certain works will only be released at a given point in time. Okay. Right. Magnets. Magnets are materials that produce a magnetic field of their own. We use the effects of the magnetic field in many ways. Various tapes contain a reel of magnetic tape. Audio cassettes also rely on magnetic tapes. Credit, debit, and ATM cards rely on magnetic strips. TVs and computer screens using vacuum tube technology. Now, this is somewhat dated because we got plasma tubes now, we got LCD tube now, and we got OLED tube and so forth. So take this in addition to the additional technology which is in place for today. So make sure that you look this up and you add that list to these items as well. Okay, do not just take this as face read. It will not be appropriate, as this was done some time before, probably a OLED TV came on the scene. Okay, some electric motors rely upon a combination of an electromagnet generators. It converts mechanical energy into electric energy. Transformers are devices that transfer electric energy between two windings. Okay, so that in itself creates an magnetic field. Okay, so use that to your advantage. Do not assume that what you read here and what you see here is the end all and be all. Expand, do some groundwork, look for the search, put it into the web, make it your business to find out. Okay. Right, lines of magnetic flux. Like poles repel each other, unlike poles attract each other, and you've seen this somewhere along the line. Only here now we're now showing you in the north pole repelling each other, and not N and S pole, north and south pole, being attracted. Okay. Now again, I can recommend you put pen to paper, make little sketches for yourself. Do not just take it off the screen and think you're going to remember it. It does not work like that. You will have your own style of learning. You will develop your own style of learning. You will implement it for yourself, and you can bring that and make that work your own. Don't just take it off the screen. When two N poles or two S south poles of a magnet are together, the magnetic flux lines are pushed outwards, away from each other. When N and S poles are placed together, the magnetic flux lines are straight and are attracted to each other. Okay? That is simple enough for you to understand. Bar magnet. And here we have a bar magnet, okay? The drawing shows the sort of pattern you would see from a bar magnet. Now, you would have done this in school with the paper, putting the magnet underneath the paper with the iron filings, okay? If you haven't done that, well, you might have done something more sophisticated today. Okay, like put a current through a coil that with a paper over the magnetic field, and you will see the iron filings take on the shape of the bar magnetic flux. Okay, now I just for me here it's a bar, but if in your case it could just be a circular bar or anything of the sort that is a magnet. Okay, the amount of lines of flux in any particular area is called the flux density. The line of flux appears to go through the north pole of the magnet, round the outside, and enter into the south pole. If the lines of flux were close together, you will have a strong magnetic field. If they are further apart, then the magnetic field is weak. So the closer you can bring your magnet to an object, the more stronger your magnetic field will be. But the further you take it away from it, the less strength the magnetic field will have. And I said to you earlier, thinking of magnetic fields, if we could develop one around your car when you're driving, so forth, wouldn't that be something? But again, it's just my imagination running wild. And here's a brilliant illustration of flux density. Okay. Here we have flux density. Now again, remember, you cannot see what I'm looking at, but you will need to go through the video I've told already what it is from the start. The amount of lines of flux in a particular area is called magnetic flux density. And here we have plate having unit area, direction of lines of magnetic flux. Okay, we have a south pole here, and we have a north pole being attracted here. Okay, north and south pole. So lines of magnetic flux. So we have our flowing from north to south. Okay, our magnetic flux is flowing north to south. Okay, north to south. And here we have an idea of how, if we have like we've simply used a table here to give us low flux density, which is just two little dots. And we have lines of flux showing us the line of flux in the direction now. Line of flux always goes from north to the south pole. And then we have a full square here with high flux density. Now the diagrams show the idea of flux density being based on area. Now what we're saying here, excuse me, is that the smaller, sorry, the smaller the area, the more condensed your flux density will be, or the stronger the magnetic field. So the more lines of flux, the more lines passing through the unit area, then the stronger the magnetic field is. Okay, that's just another way of putting it. Excuse me, I apologize. Now the flux density symbol is phi. Unit is the Weber, WB. The flux density symbol B. Unit is the Tesla or Web per meter square, etc. So the flux density equals F over A. I repeat, flux density equals B equals F over A. B equals F over A, okay? And B represents flux density. Okay? Now this is important for you to look at for yourselves, and again, do some additional research, because we have a lot of information now on the web which will give you probably a wild explanation. I won't bring it into here right now, because I think I want you to deal with this first. But again, put pen to paper, make your little sketches, take it with you. Okay. Sorry, let me just see if I can bring this up a little bit. Okay, current carrying conductor. When a conductor carries a current, a magnetic field forms around it. Now, it is important that you recognize that. So you never run a single conductor by itself because it will create a magnetic field, and that can cause problems in itself. So you will run two conductors at any point in time. One is the live, one will be your neutral conductor. Never run a live conductor on its own. Okay, here we have direction of current flow, okay, magnetic field, and we have a copper conductor here, okay, and we have 1 amp flowing with a respective volts to drive the current. And you can see that the magnetic field is set up around it. It's circulating around that conductor. Okay. The magnetic field is circular and extends along the length of the conductor. For however long that conductor is, that magnetic field will be there, will extend to the full length of the conductor, irrespective of how long that conductor is. Okay. The corkscrew or right-hand thread rule. I mean, I'll be honest with you, I've always had problems getting this. So what we've got here is there are arrows showing the direction of the magnetic field around the conductor. The direction of the field and north to south can be determined using the corkscrew or right-hand thread rule. And here we have, okay, again, you cannot see it on this, but you need to look at the video for yourselves, okay? Direction of corkscrew, direction of magnetic field, okay? And it's something like, I never get it quite right, but let's see what we can do with it. But better still that we've got a diagram to show you. If I turn the corkscrew clockwise as into a bottle, then the current and the magnetic field is assumed to be flowing clockwise. If I unscrew the cork anti-clockwise, then the current and magnetic field is anti-clockwise. Okay. But what that means is that you will simply be reversing the polarity of any current flow in regards to changing the current from one direction to another. Okay. Solenoids. Now, a solenoid occurs when a number of strands of wire are formed into a series of turns with nothing in them but air. So what we're saying here is that we get a roll of paper. Let me just see if I can do this briefly. We get a roll of paper. And we form a former, okay? So that's my roll of paper. And around that roll of paper, I put windings around this roll of paper, okay? I put windings around it, wire around it. And I keep both ends free, okay? And then one of those ends will be my positive and one will be my negative, okay? Okay, so if the turns of wire are wound around a core, it is termed as a coil. So we're producing a coil when we do that, okay? And here we have the supply current, run on A core. Now this will be an A core solenoid. If each turn of the coil is a conductor, then increasing the number of turns increases the strength of the magnetic field. So we can increase the strength of a magnetic field by increasing the number of turns we have on a former. So we could put 100 turns, for instance. And then if you increase that to 200, then you can imagine that your solenoid or former, well, solenoid would become very strong. It will be able to become very effective. Okay. And here we're looking at the what's called the right hand grip rule. Let me run that again. Right hand grip rule. Right, direction of current flow from back to front, from points towards the North Pole. So that's the idea of the right hand thumb rule. Okay, something like that. You guys probably do it better than myself, but that's the idea. Okay, let me see if I can get it in camera. Yeah, something like that, basically. Anyway, okay. To determine the direction of the magnetic field, assume that the fingers on the right hand are showing the direction of current in the coil or solenoid, and that the thumb is pointing north. Okay. Drawing current flow. So what we're saying here is simply drawing a diagram to illustrate current flow in a conductor. Okay. So here we have the cross, which means that it's going away from me and it's going clockwise, and we have the dot, which is coming towards me and it's going anti-clockwise. So when drawing the direction of flow on paper, it should be drawn as shown in the diagrams. The dot indicates that the current is coming out of the paper, which means that it's coming towards you. The cross indicates that it is flowing into the paper. Think of it as a dart with a point at one end and a flight at the other. Okay. Current flowing away means the magnetic field is clockwise. Current flowing towards means the magnetic field is anti-clockwise. Okay. Current flow in conductors. When current flows in opposite direction, the conductors A and B will repel each other. And here you have your conductors. Okay. As magnetic fields never cross, this places a force on the conductor. So it's now interesting, isn't it, to notice that although we have copper conductors and we take out 2.5, 1.5 millimeter conductors as simple, when current flows through these conductors, there's actually a force exerted against these conductors themselves. And that is something that has to be taken into account. Because if, for instance, you got a short circuit, you can imagine what would happen to that conductor in respect of that force. It will simply rip the conductors apart. Current flow in conductors again, continue. When current flows in the same direction, the conductors A and B are attracted to each other. Okay. The lines of magnetic flux between the conductors decreases, but the overall magnetic field increases. This can cause eddy currents to build up in steelwork and overheating to occur. Okay. So here we have current flowing in the same direction. Now, why am I thinking of something about two conductors canceling out each other? Oh, it'll probably come to me later on. Now, this is what we have here when we call eddy currents. Now, we're looking at eddy currents. When a number of current carrying conductors pass through a metal plate, this could be in a consumer unit or the edge of metal trunking, etc. Eddy currents occurs, okay? Now, this situation here, what we have here, we have a conductor, single conductor, carrying current just one direction. Let me make sure, no, okay. Here we're looking at line conductors, okay? We were read in this when this work was done, but you know, live conductors are now brown, okay? So please be aware, use the correct rectification and recognition for your cable conductors as they are. This work was done probably before you were born. Circulating eddy currents, okay, here, and a steel plate. Now, as current passes through the conductors, a magnetic field is induced in the steelwork. This current circulates continually unless stopped. Now, that eddy current here creates heat. And the problem here, this gets hotter and hotter and hotter. And you can imagine, especially if you be drawing a lot of load of these cables, that heat will generate. Now, what's going to happen to your insulation if it's coming from a metal frame, especially? And that is why within your framework here, once the cables come through the hole, that hole should be insulated with a plastic rim or something of the sort to prevent these conductors, even if they melt, touching the metalwork. Okay, but as you can see, what will happen is that insulation will break down, it will touch the metalwork, and it will simply trip your circuit breakers, or even worse, if the circuit breakers don't trip, cause you to have a fire. Not in your best interest at all. Okay. How do we deal and remove eddy currents? Now, we remove and deal with eddy currents by ensuring that we run a positive and a neutral together within the same framework. That neutralizes eddy current and prevents that. Also, something we can put slots in here which will break up the eddy current and prevent it from becoming an issue. So we run live and neutral together, irrespective of our circuits. Okay? And that makes us ensure that we are not producing eddy currents unnecessarily. Okay? Let's just go in and make sure that you can pick that this up, okay? Just make sure we come back and framework on this. Okay, yes, okay, good. Okay. And here we are coils, okay? Now, like the solenoid, you can say it's a similar thing, but we turn our coils. If we want to use the extra magnetism that comes from having the current passing in the same direction, we use a coil. And we can use a coil former A code. Now, let me just go back a little bit and show you where we were. How far am I? 1 second. How far? Here. Now, if we turn this this solenoid upside down, that we can begin to bring that as a coil as well. Okay. So we can look at that from here. If we turn it around, okay, that could also become a coil. So it's just looking at it from a different angle. So coils, if we want to use the extra magnetism that comes from having the current passing in the same direction, we use the coil. Okay, and that's what's saying. This is an A-filled coil with very few lines of magnetic flux, purely because of the number of turns we've put on the coil. The type of material used as the former affects the strength of the magnetic field. Normally, the coil will be run in an iron core, which, when you use an iron core, it causes the magnetic field to become stronger. And here we have copper coil, okay? A coil former made out of copper has more lines of magnetic flux than one of air. So in comparison to the copper coil and in comparison to the air coil, we get more flux density from the copper than we would from the air. Because the copper enhances the magnetic flux density and makes it more condensed and concentrated, therefore making it stronger. And here we have an iron former as well. So here we're using iron instead of copper. So let's just go back here again. We're using, instead of using copper here, instead of using copper now, we're using iron, okay? Let me just confirm that it is iron, yes. It is an iron former, yes, okay? So here the former here is made out of iron, and there are many more lines of magnetic flux than you would have in the copper, okay? Iron is a very good former in regards to electromagnetic flux. This understanding of the way magnetic fields affect cables and metals should help you as an electrician to decide which cables, etc., are best placed where and why they shouldn't be placed in some other situations. Okay? And again, remember that eddy current is a dangerous thing to have around and needs to be neutralized at all points in time. Okay? Right. I hope you found this useful, and have a good day. Bye-bye for now. Okay. Have a good day. Bye-bye for now. Thank you.